this is section 2.2. It's all about just the basic rules for finding a derivative. So let's start with a clarification with notation. Let's talk about the difference between f prime of x, here's an x, and f prime of c. Now, c represents any constant, so it might be, this is like saying the derivative at 2 or the derivative at 1. Okay, the difference is that f prime of x, that's the equation. Okay, so it's the generic equation for the derivative anywhere on the curve, okay? So that's the generic equation. If I want to know the specific slope at a point, like the slope at 2 or the slope at 1, that's the f prime of c. So this is the slope of the curve at a specific point. So basically this just means I've plugged a specific number into my derivative equation to find the exact slope at a particular point. Okay, so let's talk about just basic derivative rules. First of all, if you have y equals some function, some constant, it might be y equals 2, y equals 3, y equals 5, okay? If y is just a constant, then the derivative is 0. Because, think about it, if y equals a constant, isn't that just, if it's y equals 3, isn't that just the graph of a horizontal line right here at 3? And if it's a horizontal line, don't we know that the slope is always 0? So the derivative of a constant is 0. If we have, let's say, y equals some constant times x, so that might be y equals 2x, y equals 3x, y equals 5x. Again, isn't that just a line? And if there's no plus b, then it's some line that goes through the origin. But isn't the slope just whatever that number in front of x is? Think of it as mx, okay? So in this case, the derivative is just whatever that constant is out in front. So the derivative of 2x is 2. The derivative of 10x is 10. Excuse me. All right. Here's the big one. This one is our exponent rule. All right. If we have y equals some power of x, it might be x squared, x cubed, x to the 10th, x to the 1/2. It might be x to the -2. It doesn't matter what the exponent is as long as it's a number, right? A fraction, an integer, a positive, a negative, doesn't matter. So in that case, in order to find the derivative, it's going to seem a little strange at first, but then I'll give you an example, and it's not hard to do. So what we do is whatever the exponent is, you bring that down in front as a constant, bring that number down in front, you keep the x as your base, but then you decrease your exponent by 1. Okay, again, I know it looks kind of strange, but let me show you an example. Let's say I have, let's just go with an example of, let's say I have y equals x to the 4th plus 3x plus 2. Okay, so the derivative is, so for x to the 4th, that's a power of x. You bring the 4 down in front, you keep the x, and then you decrease your exponent by 1, and so you get 4x cubed. So that was an example of a power of x. I just did the derivative of x to the 4th. Okay, let's go to the next term. So I'll bring down the plus. Well, that's just a constant times x. And up on number 2, we said the derivative of a constant times x is just that constant. So that's just 3. And then finally, I have this plus 2. Well, remember, if it's just a constant and there's not an x with it, the derivative is just 0. And no, you didn't need to write that. I just wanted to show you I did the derivative of each individual term there. Okay? My next rule, and it's kind of one of these rules that you would assume to be true even if I didn't tell you. And basically this one says, if you have some constant in front of a term, so maybe it's like a 3 in front of an x squared, or a 10 in front of an, x cubed, right? Some constant in front of a term. Then basically when you're doing the derivative, you leave that constant alone, and then you just take the derivative of that term. Okay, an example here might be, let's say we have y equals 10x to the third. Okay, so there's a constant 10 in front of a function of x, x cubed. So the derivative is, leave the 10 alone, and then take the derivative of x cubed, which would be 3x squared. And yes, I can simplify this to be 30x squared. Now, some people get confused because they're saying to themselves, well, I thought the derivative of a constant was 0, because remember, number 1, we said the derivative of a constant is 0. But that's when that's all there is, right? Like up here on the 2, that number was not in front of an x term. Okay, so number 4 is talking about if you have a constant in front of something else, not as it is standalone. Okay? And then another one that we're going to write as a rule, and you're going to just assume it would have been true even if I didn't tell you, because we've already used it, and that is if you have separate terms being added or subtracted together, kind of like we did up on that first example, then in order to do the derivative, well, what did we do up there? We just took the derivative of each one separately. So you would take the derivative of that first one separate from the derivative of the second one. Again, you're going to assume that to be true because I did it up here and you never thought anything about it. Okay? And this is honors calculus, so we're not doing trig. So those are the basic rules. So let's apply that to a few problems. Okay, look at number 1. Well, I've got several terms all being added and subtracted, so that means I can just do the derivative of each one separately. So the derivative of the x to the 5th, bring down the 5, keep the x, decrease it by 1, plus, okay, the 2 is in front of the x cubed, so I'm going to leave the 2 alone. And when I do the derivative of x cubed, won't I bring the 3 down in front? So I'm just going to go ahead and multiply that by the 2. And then I have my x, decrease your exponent by 1. Okay, bring down the plus sign. Same thing here. When I bring the 10 down in front, it's just going to multiply by the 4. And then I decrease my exponent by 1. Plus, all right, this is just a constant times x. So that was the second derivative rule, so that's just 10. And then remember, this is just a minus 20, so the derivative is 0. So I won't even write it down. So that is my overall derivative. Okay. Now I want to show you something on number 2. First of all, well, I could combine these because they're all like terms, but I want to show you something. Forget the 2 over x and the 5 over x. Just look at this x to 1 over x. I want to show you something. If I think of that, because I can't do the derivative of that like it is. It's a fraction, and I don't have any rules for derivatives of fractions right now. So I'm going to think of that as x to the negative 1, because now it's just a power of x. So if I do the derivative of that, and I'm not going to call it g prime right now just because I'm just doing this one term, then I would bring the negative 1 down in front. I would keep the x. And when I decrease that by 1, right, when I subtract 1, my new exponent is negative 2. So the derivative is actually negative 1 over x squared, right, because we don't keep negative exponents. So I just showed you how to do the derivative of 1 over x. But the reason I did this separately is because I want you to look at this and kind of memorize it as one of our rules from the other side. Because the derivative of 1 over x comes up so often, I don't want you to have to go through, this work of coming up with the derivative. I just want you to know it. And now that you know it, let's go back to number 2 here. Okay, if I want to do the derivative of this whole thing, I will say, well, we just said the derivative of 1 over x is negative 1 over x squared. Okay, but 2 over x, apply the same rule, is going to be negative 2 over x squared. Bring down the minus. And then 5 over x, apply the same rule, it's going to be negative 5 over x squared. And yes, I know you can turn this into a plus, but I just wanted you to show I could apply that same rule, whether it's 1 over x, 2 over x, or 10 over x, it doesn't matter. Okay, so that is my derivative. All right, look at number 3. Now, before you start bringing that 3 down in front, be careful. I don't have a rule for parentheses. None of these rules that I gave you over here had parentheses on the terms. Okay, so before I can do the derivative, I have to get rid of those parentheses. So I need to think of this, cube both of them. I need to think of this as 8x cubed Now it is something that I know how to do the derivative of. Bring down the 3, 24x squared. So sometimes you have to change the way it looks before you can do the derivative. Like, for example, on number 4. Again, I don't have a rule right now for doing the derivative of a fraction. I mean, if it were just a 4/3, that's a constant. I'm not thinking of that as a fraction. But the fact that there's an x in the denominator, I can't do that derivative. So I'm going to think of this as 4/3 and then x to the negative 2. Now it's just a constant times the power of x. So I'm going to say the derivative is, bring down the negative 2, multiply it by the 4/3, so negative 8/3, and then decrease your exponent by 1. If I decrease it by 1, it becomes negative 3. And I don't want to leave any negative exponents, so I'm going to write this as negative 8 over 3x cubed. Okay, 2 more. Take a look at number 5. Again, I don't have any rules for doing the derivative of a square root, so I need to think of this as x to the 1/2. Now I can just use my exponent rule. Bring down the 1/2, keep the x. If I decrease my exponent by 1, it becomes negative 1/2. So I'm going to think of that as 1 over 2x to the 1/2. I just don't want to leave any negative exponents. Okay, on this one, I don't have a rule for doing fractions. I don't have a rule for doing cube roots. So would you agree that cube root of x is the same as x to the 1/3? And since I don't want it in the denominator, right, in order to bring it up, it would just make the exponent negative. So I'm going to say the derivative is, bring down the negative 1/3, keep the x, and when I decrease this by 1, my new exponent is going to become negative 4/3. So I'm going to think of this as negative 1 over 3x to the 4/3. Okay? So take a look at number 8. Oh, it looks terrible. So before I start doing the derivative, notice I'm not labeling this as derivative right now, but I'm just going to clean everything up. So that first term, I'm going to think of that as x to the 2/3. The next term, I'm going to think of that as x to the negative 2. Now let's see if you can handle this. There's my minus. If I square that denominator, it's going to be 9x squared. So I'm going to think of this as 2/9, because I'm leaving the 9. It's the x squared that I'm going to bring up and have a negative exponent. And then I still have pi squared. Notice I didn't do the derivative yet. All I did was clean it up. Now I'm ready to do the derivative. Bring down the 2/3. Decrease your exponent by 1. Let's go to the next one. Actually, I won't write a plus, because when I bring down that negative 2x, decrease your exponent by 1. Now, I'm on, just so that you're all keeping up, this is where I am right now. When I bring down the negative 2, won't that become a positive 4/9? And then when I decrease my exponent by 1, it's going to be to the negative 3. And this one tends to trick people. A lot of people will say, oh, it's plus 2 pi. But remember, pi is not a variable. Pi is a constant. I mean, it's like 2.7. It's almost 3. So really, this is just kind of like having a plus 9 at the end. And if it's like a plus 9 at the end, then the derivative of that is nothing. Okay? So to clean this up, because we don't like to leave negative exponents, we're going to say the derivative was 2 over 3x to the 1/3 minus 2 over x cubed plus 4 over 9x cubed. Okay, and look at number 9. Common mistake for people is to just do the derivative of the top and then do the derivative of the bottom and call it done. But that's not how it works. We don't have a rule for doing the derivative where we have x's in both the numerator and denominator. No rule for that yet. So I need to somehow turn this into individual terms. Well, think about it this way. What's being divided by x? Is it the 3x squared or the 2x or the 5? And hopefully you're going to say, well, all of them are. It's the 3x squared that's being divided by x, and it's also the 2x that's being divided by x. I need to scooch this a little bit. And it's also the 5 that's being divided by x, right? Okay, so let's simplify that. What I really have, again, I'm not doing the derivative yet. I'm just simplifying. 3x squared over x is 3x. 2x over x is 2. and then I'll leave the 5 over x. Again, I have not done the derivative yet. I've just simplified. Now I'm going to do the derivative. The derivative of 3x is 3. The derivative of 2 is nothing. And look, 5 over x. Isn't that the thing I said, hey, just get to know the rule? If the derivative of 1 over x is negative 1 over x squared, then the derivative of 5 over x is negative 5 over x squared. Okay? So those are your basic derivative rules with several examples.